In this lecture, we will prove Poisson's metrization theorem. So, first, some preliminaries. So, let X be a metric space. So, define a function d prime on x cross x by d prime of x comma y is the minimum of d of x comma y and 1. So, where d is the metric. Then d prime is a metric and it induces the same topology on X as D. So proof: if D prime is a metric, then the open balls B D prime x comma r when so let me write as B D prime x comma r is equal to B D x comma r when r is strictly less than 1. Thus, it is clear that both will generate the same topology. So it suffices to show that D prime is a metric. So if D prime x comma y is equal to 0, so then this implies that, so since minimum of D of x comma y and 1 is equal to 0, which implies that D of x comma y is equal to 0, which implies x is equal to y. So this is equally easy. So let us show that D prime x comma y is less than or equal to D prime x comma z plus D prime z comma y. So if this quantity on the right is greater than or equal to 1, then there is nothing to prove. So assume that D prime x comma z plus d prime z comma y is strictly less than 1. So in particular, this will imply that both of them individually are strictly less than 1, which will imply that d prime x comma z is equal to d of x comma z, and d prime z comma y is equal to d of x z comma y. And as d of x comma y is less than equal to d of x comma z, plus d of z comma y, this implies d of x comma y is also strictly less than 1, which implies d of x comma y. So it follows, so this implies that this proves the lemma. So let us take R with a standard metric and apply the above lemma. To define a new metric d prime and we use the above to define a new metric, a metric on Rn. This is the product indexed by natural numbers. So we need to show that this is indeed a metric. The function d defines a metric on Rn. So clearly, this holds. So if d of xy is 0, so this would mean that the supremum of the distance between xn and yn is divided by n is 0, which means that each of them are 0. So this implies that x is equal to y. So let Rn then d prime xn yn divided by n is less than or equal to d prime xn zn divided by n plus d prime zn yn divided by n. So using supremum of I ai plus bi is less than or equal to supremum over I of ai plus supremum of I bi, we get So this proves that T is a metric. So theorem, the metric T induces the product topology. So proof. So let us first show that every open set in the product topology is open in the topology induced by D. So let us take a point in this product, a basic open set in the product topology. Looks like so K is a natural number. This consists of those tuples such that T prime of xj comma yj is strictly less than epsilon for j lying between 1 and k. So let y be a point in this open set. So choose a delta between 0 and epsilon by k so that this ball byj comma delta is contained in b xj comma epsilon for j lying between 1 and k. So for each j between 1 and k, this distance is epsilon and yj is contained in this ball. So we can find a delta small enough so that this happens, and then since there are only finitely many j's, we can find a delta small enough which works for everything. So then we claim that p d y comma delta is contained in u x k epsilon. So let us check this. So suppose z is a point here. So this implies that t zj comma yj divided by j is strictly less than delta. So this implies that t prime zj comma yj is strictly less than j delta, which is less than or equal to k delta, which is strictly less than epsilon for j like between 1 and k. And this is precisely the defining condition for u x k epsilon. So which implies that So this shows that every open set in the product topology is open in the topology induced by tau, induced by D. So now let us prove the converse. So now let D x epsilon, so let's write it as BD. So this is the ball with the metric being capital D, P an open subset. So it suffices to show that there is a set U xk epsilon, xk delta such that is contained in BD x epsilon. So this will show that every open set in the topology induced by D is open in the product topology. So why is this true? Is left as an easy exercise. So in order to do this, so choose K such that 1 upon K is strictly less than epsilon by 2. So then we claim that U xk epsilon by 2 is contained in P, is contained in this ball. So let us check this. So if Z in this is in this, so this implies that D prime is strictly less than epsilon by 2 for j lying between 1 and k. So this implies D prime xj comma zj divided by j is less than 1 upon j times epsilon by 2, which is less than equal to epsilon by 2. So, and this if j lies between 1 and k, if j is strictly greater than k, then d prime xj zj by j is strictly less than 1 upon, less than equal to 1 upon j, which is strictly less than 1 upon k, which is strictly less than epsilon by 2. So thus when we take supremum, is going to be less than equal to epsilon by 2, which is strictly less than epsilon, which implies d of so this implies so this proves that both topologies are the same. So using this theorem, we will prove Ulrichen's metrization theorem. So let X be a regular topological space which is second countable. Then X is metrizable. So proof. So as Rn is metrizable, so this is Rn with the product topology. It suffices to produce a continuous map f from X to Rn such that 1 f is an inclusion and 2 f from X to f of X is a homomorphism, or rather is an open map where f of X has a subspace topology from Rn. So let us do this. So if you do this, this will imply that X is homomorphic to f of X, where f of X has a subspace topology from Rn. And since the topology, the product topology on Rn is coming from a metric, this will imply that the topology on f of X is also going to come on from a metric, which will imply that the topology on X is coming from a metric. So to prove this, so let B be a countable basis for the topology on X. So consider pairs V comma U such that V and U are at B and V closure is contained in U. So then by Urysohn's lemma, there is a continuous function f v comma u from x to 0 1 such that f v comma u of v closure is 1 and f v comma u of x minus u is 0. So we have a countable collection of continuous maps from X to R, and we put them together to get, so put them together to get a continuous map f from x to, so there is the product over all pairs v comma u that we took above, r, and this is a countable product. And this map is given by x gets sent to the tuple fv comma ux. So recall that to give a continuous function from x to a product of topological spaces, it suffices to give continuous functions to each of these topological spaces. And here each of the coordinate functions is continuous, and therefore this map is continuous. So first, so clearly this map is continuous. So let us prove that this is an inclusion. So if x not equal to y are points in x, then there exist basic open sets v comma u such that x belongs to v is contained in v closure is contained in u, and y does not belong to u. So then when we look at this function fvu, we get fvux is 1 and fvuy is equal to 0. So thus f of x and f of y differ in the coordinate corresponding to this pair v comma u. This implies f is an inclusion. So finally, we need to show that x f of x is an open map. That is, we need to show that if u contained in x is open, then f of u is open in f of x, where f of x has a subspace topology. So to do this, it suffices to show that if x is in u, then there is an open set y contained in this product such that f of x is in y intersected f of x, and this thing is contained in f of u. So let us do this. So for this, we find basic open sets w and w prime such that x belongs to w is contained in w closure, this contains W prime, which is contained in U. So now consider the projection. Pi W prime from this product to R, and let, so we are just projecting onto the coordinate corresponding to W prime, and we let y be equal to pi inverse of 0 infinity. So by definition of f, pi W prime compose f is equal to this function f W prime. And as x belongs to W closure, this implies f W prime of x is equal to 1. So which implies that f of x belongs to pi W prime inverse of 0 infinity, which is by definition y. So this implies that f of x belongs to y. So this implies that f of x belongs to y intersected f of x. Now suppose f of a belongs to y intersected with f of x. So this implies that f w prime of a belongs to 0 infinity, which implies that y belongs to w prime, which is contained in u, not y. So a belongs to w prime, which is contained in u, as f w prime is 0 on x minus w prime. So this implies that y intersected f of x is contained in f of u. So because we took a point f of a in this intersection, and we proved that f of a, so let's write this. So as a belongs to u, this implies f of a belongs to f of u. This implies that y intersected f of x is contained in f of u. So this proves